Okay, so the next topic is how are concurrent programs developed in Java? And we're going to talk about how you can do this with Java. We'll start by talking about the way it's been done in the past, which is by using things called threads. And each thread in Java has certain interesting state we'll talk about. And this is the historical way of doing things. And then there's something that's coming just around the corner. It's looming in the future called Project Loom. And this is changing the way in which threading can be done in Java. And I'll just talk a tiny bit about that. That's not going to be a big focus in this course. We'll probably talk about that more in the spring. Hopefully in the spring, the Java support for this thing called Project Loom will be more advanced and more easily accessible than it is right now. So in classic Java, what is a thread? In classic Java, a thread is an object. Pretty much everything is an object in Java for the most part. And what does that mean? Well, it means it contains methods and has some fields. Now, you only see the public methods for a thread. Here's a summary of them in a UML diagram-like form. You don't really get access to any of its fields. And historically, each Java thread has a unique stack, which traditionally had a one-to-one mapping with an operating system thread. We'll talk a bit more about that in a second. That's an important distinction for future Java. It also has other characteristics, like it has registers that it used to keep track of things like the stack pointer and the frame pointer and other things that you need to do concurrent execution or instruction stream processing. It also has something called thread-specific storage, or so-called thread local storage, which is another feature that Java has. So that's kind of the classic way things work, and you can take a look at this link for more information about what's in a Java thread. In forthcoming Java, in Project Loom, which you can get access to with the early access version of Java. You can, and if you go to this link, you'll see the description of this particular modern thread. They distinguish between two variants of thread. The legacy threads, the historical threads, traditional threads, are called platform threads, and a platform thread has a stack. That's an operating system stack for each Java thread. Each platform Java thread. Virtual threads, in contrast, are the new enhancement to Java. And that adds lightweight concurrency. And basically the idea is, unlike a traditional platform thread, which has an operating system stack, which takes a fair amount of memory, virtual memory for each thread, virtual threads take almost no memory at all. An operating system thread has typically got about a megabyte worth of virtual memory associated with it. A virtual thread has about a kilobyte of memory associated with it, so it's very, very small. And essentially you can have hundreds or thousands or millions of Java virtual threads, and that allows you to do a lot of things in a very conventional, convenient way without having to deal with all the complexity of asynchronous program. So we'll talk more about that later. It's a little outside the scope of this course, but I just want you to be aware of that. And virtual threads are actually multiplexed on top of a small number of so-called carrier threads, which are like worker threads, of which there are typically about as many as there would be cores on your underlying processor. So you might have 8 cores on your processor, so you have 8 carrier threads that are platform threads that actually are doing certain types of computations, and then your virtual threads can number in the hundreds or thousands or millions, and most of them are just sitting around getting a chance to run. So again, it's a little beyond the scope to go into this in detail, but I want you to be aware of it because future discussions of Java concurrency will start to be informed by these newer features that are coming along. A traditional Java thread can be in a number of states. So when you create a thread, it is in the new state. When you start the thread, it becomes runnable. When the scheduler decides it can run, it becomes running. And then various things can happen while it's running. It might be blocked, trying to access some guarded resource like a synchronizer. It might go into a sleep for a certain amount of time. It could wait by doing some kind of wait operation. And at that point, it'll be suspended and some other thread will get a chance to use the core, and when whatever it's waiting on is finished, it gets a chance to run again, and when it's all done, it terminates. When the run method is finished, the thread is gone. So that's a quick summary of the states in a classic Java platform thread. There's also a very interesting number of states in virtual threads, which I will not go into much detail on because it's beyond the scope of the class. But if you're interested in learning about virtual threads, take a look at this link below. It's a guy named Heinz Kabutz, who is an expert on Java concurrency, and he's been working with Project Loom and the development of Java virtual threads. So there's a bunch of other states. Concurrent Java threads interact using either shared objects, I'll talk about what that means in a second, or message passing. And I like to use little icons. This means message passing, and this means sharing. It's like the share icon. What are shared objects? Shared objects are basically synchronizers that ensure concurrent operations running in different threads obey certain properties. Most importantly being that they're not all running and accessing shared mutable state at the same time. That's what a synchronizer's primary purpose is. It's there to make sure that for so-called critical sections of code where you only want one thing to happen at a time, you have a synchronizer, and then threads that want to access that critical section take turns acquiring the synchronizer, doing their thing, and then releasing the synchronizer, and then letting someone else come in. I'll talk about metaphors for this. A good metaphor for this would be a restroom on an airplane, where they have the two states occupied and available. And so, when you go in, you shut the door, and it goes from one thing to the other. So that would be an example of a synchronizer. There's a bunch of examples of synchronizers. The properties, however, that they all enforce will either be mutual exclusion or coordination. So what is mutual exclusion? Mutual exclusion means that interaction between threads will not corrupt shared mutable data. And what that means is that, again, if multiple things are trying to access something, that they take turns and only one is in there at a time. Again, think like the restroom in an airplane. Coordination, or cooperation, but let's call it coordination, is going to be used to ensure that operations occur at the right time, in the right order, and under the right conditions. And so this is really about coordinating how things run and when things run. And there are different mechanisms to do that. Typically, mutual exclusion in Java is done through either synchronized statements or reentrant locks or other lower level things like spin locks. And coordination is typically done by something called condition objects. Here are some examples of Java synchronizers. So we have synchronized methods and statements. You may have seen these if you've done much concurrent programming in Java. Reentrant locks, atomic operations, semaphores, condition objects, and at the very low level, the so-called compare and swap operations, which are things that are typically baked into the hardware on the instruction set of the processor and are at the heart of all the things that take place in Java. We're not going to spend much time talking about any of these things. That'll be in the spring. You'll learn more than you ever wanted to know about synchronizers if you come to the spring class. The alternative way to have threads interact is by passing messages. And in this context, we're going to send a message from a producer thread into a queue, and then another thread will take that message when it's got access to it and consume it. So you have producers and consumers, and they communicate with each other using a thread-safe queue. Examples of these in Java would be array blocking queues and linked blocking queues, priority blocking queues, synchronous queues, concurrent linked queues. These are all examples of synchronized queues in various ways that you could use in Java. Once again, we will not talk much about these. And why are we not going to talk about them? Because one of the problems with using this style of programming is you end up with so-called concurrent programming hazards. And so what you have here is a situation where sharing of shared mutable state gets you into trouble and can cause all kinds of problems with your code. Here are the most common problems. One is called race conditions, and race conditions can occur when a program's correctness or a proper operation depends on the sequence or the timing of threads for it to operate properly. And you can take a look if you want to see an example of race condition that I did intentionally. There's an example in my GitHub repository that has producer-consumer threads sharing a queue that lacks any synchronizers. So as a result, when the threads are putting and taking things from the queue, it's scrambling up the internal state, and chaos and insanity ensue, and you get all kinds of weird errors. So race conditions, big problem, one of the common mistakes you get in a concurrent program. Other problems you get in concurrent programs have to do with memory inconsistencies. And this occurs because modern multi-core processors have caches to speed things up. And those caches don't get flushed and coordinated unless you use synchronizers properly. And if you fail to use synchronizers properly, you can end up with problems with atomicity or consistency or visibility or ordering, all these low-level strange problems that are very difficult to detect and very difficult to debug. So it's because different parts of your program have different views of memory that's being cached. My example here that I like to use would be, if anybody here is a Star Trek fan, if your Star Trek transporter goes awry, you transport half of someone somewhere and the other half stays back. So you end up with like inconsistencies with your state. For those of you who are Harry Potter fans, if you remember splinching from Harry Potter, where someone would apparate somewhere but they'd leave their nose behind or something like that. Very common problem apparently when you're learning to apparate. Here's a simple example to illustrate this. So here's a program that I've called Loop May Never End. It's got a Boolean called done, and we set that to false, but notice it's unsynchronized. It's just a good old Boolean. There's nothing special about it. And then down here in thread T2, we're going to read from whether or not this thing is done, and it'll just keep looping until done is set to true. And down here, we're going to set done to true, but because it's not synchronized, that assignment may never get pushed from thread 1's cache to thread 2's cache. So it may set it here, but this will never be updated because they have two different views of the same piece of memory. So nasty problem, you don't want to have to deal with that. Another nasty problem you don't want to have to deal with is deadlock, which occurs when two threads are competing for resources and they both wait for the other to finish, but neither one will release what they have. So here's an example. It's also sometimes called the deadly embrace or circular wait. So we have two threads, thread T1 and thread T2, and we'll say for sake of argument that thread T1 owns lock L1 and thread T2 owns lock L2, and thread T1 wants or needs L2 and thread T2 wants or needs L1. And of course, this guy is holding on to L1 and won't release it. This guy wants L2, but L2 is owned by T2, which won't release it. So they've got a deadlock. That's also a very subtle problem. There's ways to break deadlocks, but they're a little bit tricky. So as a consequence, these two threads will be stuck forever in a deadly embrace. And I have an example here in my GitHub repository to show how to deadlock if you'd like. There's other issues as well, but the long and the short of it is that concurrency leads to trouble, and concurrency leads to trouble because we're sharing mutable state. And what we're going to talk about next time we get together on our next class on Monday is how parallel computing doesn't have these problems. How could that be, you might ask? Well, the reason it doesn't have these problems is because it doesn't share data for the most part. Or if it does it in a very, very limited and controlled way. So as a consequence, by not sharing data, most of the things we just talked about, race conditions, memory inconsistencies, deadlocks, disappear because we're not sharing anything. And of course, the other big benefit we get from parallel computing, which we'll talk about next time, is you can take advantage of all those cores. So if you've got an 8-core machine and you have a program that can be decomposed into what's called an embarrassingly parallel design, where each task runs independently, you can get an 8-fold speed up or near to an 8-fold speed up of the processing by running things in parallel. So that's the end of our overview of how concurrent programs are developed in Java.